Greetings everybody, and today we're going to be using complex analysis to evaluate the Gaussian integral. So this is going to be a bit of an exotic application of complex analysis and contour integration because we have to use a bit of a weird contour that we haven't really seen yet, as well as a weird function, and that's all just to kind of recover our Gaussian integral in the very end. But let's just jump straight into it. We'll worry about those details later on. So first of all, with contour integration, what we usually like to do is we like to define some complex valued function f of z to be equal to, and usually we just take this integrand but with a complex variable. So in this case, it would be e to the minus z squared. But the problem with using e to the minus z squared as our function is that it's actually entire, because z squared is entire, the exponential function is also entire, so when you compose those two together, it's also an entire function, and that means we won't have any singularities, and that's bad because we can't use the residue theorem. So as it is, the function as it is, it's a pretty bad function to work with, and in order to make it a good function, let's modify it. And the way we're going to modify it is by dividing by some new function g of z, some other complex function. And the idea is, well, we're still keeping this e to the minus z squared, but we have this other function g of z, and wherever the zeros of g are, it's going to be exactly the poles of our function f. So maybe we can take advantage of that for whatever our function our g happens to be. We'll figure that out later on. We can take advantage of that in order to use the residue theorem for f of z later on. So we'll just define f of z like this for now. We'll worry about more details later on, but let's take a look at the contour we might be using. Let's take a look at this interval. We want to integrate from negative infinity up to infinity. So if we draw up, let's say the top half of the complex plane, negative infinity to infinity, well, we can just consider the finite case, which is from some big radius minus r to r, like so. And we want to integrate along this path from minus r to r. And later, of course, we're going to be taking the limit as our r approaches infinity. And if we integrate along this, then maybe we can get an integral that's kind of similar to our Gaussian integral. So we want to contour integrate our function f of z, and remember we had our function g of z over here. Maybe that g of z will produce some poles, let's say over here, for example. Could really be anywhere, but it doesn't really matter. And what we want to do is we want to enclose this pole in order to use the residue theorem. And the way we're going to do that, well, we could use a semicircle that we tend to use when we work with contour integrals, but instead we're going to be constructing a box around this, or a rectangle. And this turns out to be a lot easier to evaluate, mainly because if you consider a semicircle, maybe if in the limit our radius approaches infinity, that semicircle will vanish, and then we're just left with the integral from minus r to r of f of z, but f of z isn't quite the Gaussian integral. So that's one reason why we don't really want to use a semicircular contour. We want to construct a box instead. So maybe something like that. And we're going to give it a little bit of height. The height, we're going to give it a height of b, for example. So this point up here would be r plus I times b, and this point on the left, top left over here, would be minus r plus I times b. And then of course this bottom point is minus r, and then you have r over here. Okay, and well, we're going to traverse this rectangle in the positive direction, so anti-clockwise, and let's call each of these separate paths a name. Let's call the bottom path gamma 1 and the right path gamma 2. Then we have gamma 3 and gamma 4 down here, and let's call the whole entire contour C. Alright, so we have our box set up, which is quite nice. Let's write out a couple of integrals now. So from this picture, we can clearly see that, and I'll put it over here, if we have the contour integral over C of f of z dz, we can decompose this into the integral along each of these separate paths. So this is going to be the integral along gamma 1 plus the integral along gamma 2 plus the integral along gamma 3. Do I have enough space? Yes, I do. Plus the integral along gamma 4. Okay, very nice. And notice, since maybe we're going to enclose this singularity, this pole, we can use the residue theorem. So all of this stuff is equal to 2 pi I times the sum of the residues. We don't really quite know how many residues we're dealing with. So we're going to take the sum of the residues of our function f of z. So, and those residues are going to lie inside of this box. Okay, very nice. And now we want to start figuring out what our function g of z is equal to. And in order to make it easy for ourselves to find what g of z is equal to, we have to start assuming a couple of things about our setup over here. So first thing I'm going to assume is that in the limit as r approaches infinity, the integrals along gamma 2 and gamma 4 will actually vanish. So as these vertical paths over here move out further and further and further, the integral along those paths will vanish. And if that does happen, which we hope it will, what we're left with is that the integral along gamma 1 plus the integral along gamma 3 is equal to 2 pi I times the sum of the residues of our function f of z. And technically this should be, there should be a limit as r approaches infinity out here. And obviously we're integrating our function f of z. So maybe let's try starting to plug our function into these integrals over here. I'm just going to drop the limit for now. We're just going to assume we're taking the limit. So this is going to give us the integral. Now we're starting from minus r, we're going up to r. So minus r to r of f of z dz. And then we're going to add the integral along gamma 3. And what is the integral along gamma 3? Well, we're starting up here, which is r plus I times b, and then we're moving to the left all the way to minus r plus I times b of f of z dz. Alright, and we can do a bit of a substitution to kind of fix these bounds a little bit. We don't really like having imaginary numbers there. So you can do a substitution such as z is equal to w plus ib, and if you do that, well, you're going to get the integral from minus r to r of f of z dz, and for that second integral you're going to get plus the integral from r to minus r of f of, well, imagine this w is kind of like a z, so we're going to have a z plus I times b, and then our differential is still dz. It doesn't change under this translation. Alright, and now I want to fix these bounds a little bit. We're kind of going from big to small, which isn't really good, so let's reorientate it. So we're going to go from minus r all the way up to r. And now if we take the limit on this thing, so limit as r approaches infinity, we're going to get the integral from minus infinity to infinity. We also have an integral from minus infinity to infinity here. So let's combine the integrands together, and we are going to get f of z minus f of z plus ib dz, and this is equal to, well, 2 pi I times the sum of residues. So 2 pi I, and then we have the sum of the residues of a function f of z. So notice one thing, we have an improper integral from minus infinity to infinity of some kind of function in here, and this is equal to 2 pi I times the sum of residues. This over here, we will eventually know how to evaluate. So wouldn't it be nice if our integrands over here was exactly e to the minus z squared, for example, because the left-hand side will end up being the Gaussian integral, and then we have the right-hand side which we can evaluate quite easily. So right from this line over here, why not let this integrand be exactly e to the minus z squared? So we want f of z minus f of z plus ib to be exactly e to the minus z squared. And right over here, I want to make a slight modification, because over here we're assuming that b is a real number, because this is the height of the rectangle, so we're assuming b is a real number. But the problem is, when we solve this equation, the only non-zero solution is when b is a complex number, because if we're restricting b to being a real number, the only solution is b being equal to 0, which isn't really quite useful. So instead we have to make b a complex number. So the solutions to this equation only occur when b is a complex number. So if b is a complex number, so b is in C, that means I times b is also a complex number. And why not redefine I times b as just being some complex number tau? And that's exactly what we are going to do. We're going to replace I times b with tau. Alright, and now that we have this fact, we can start figuring out what our g of z could be. So from what we have over here, f of z, well, that's e to the minus z squared over g of z. And then we have a minus f of z plus tau. Well, let's just plug z plus tau into what we have over here. That's e to the minus z plus tau squared over g of z plus tau, like so. And we want this to be equal to e to the minus z squared. Alright, and notice one thing over here. We have g of z, and we also have g of z plus tau, so it's kind of translated a little bit. This is very hard to work with. If we have some kind of expression like this, it's almost impossible to find some kind of generalized solution for our function g. So we have to make another assumption to make our life easier. Why not assume? So we're going to assume that g is periodic in taus. So g is periodic in tau, and what does that mean? G of z is the exact same thing as g of z plus tau. So let's rewrite this a little bit. We're going to have e to the minus z squared over g of z minus, and then this is divided by g of z, and let's expand out the top a little bit using the binomial theorem. So that's going to be e to the minus z squared minus 2z tau minus tau squared, and this is all equal to e to the minus z squared. And notice on the left hand side, we can rewrite this a little bit again. This is equal to e to the minus z squared over g of z. And what I'm going to do to the second term, I'm going to split it up a little bit. Notice we have an e to the minus z squared. That's kind of isolated a little bit over here as well. So this is going to be e to the minus z squared. And then using some exponential properties, we also have the multiplication by e to the minus 2z tau minus tau squared. And this is all divided by g of z. And all this is equal to e to the minus z squared. And notice one cool thing, we have e to the minus z squared, same thing over here, same thing over here. So let's cancel out everything. So this cancels, this cancels, and this cancels. And we're left with a 1 over here. So this is a 1 over here. And over here, this is also going to be a 1. Let's multiply g of z over to the right hand side. And we obtain a solution for g of z to be equal to, well, we have 1 and then a minus e to the minus 2z tau minus tau squared. So this is our solution for g of z. Not quite, but it is one of the solutions. So we've figured out what g of z is equal to. It's not quite a complete definition because we also still don't know what tau is equal to. So how do we figure out what tau is equal to? Well, we simply just use the fact that g is periodic in tau. And if g is periodic in tau, well, what does that mean? It means g of z is equal to g of z plus tau. So g of z is equal to g of z plus tau. Let's use our definition of g of z that we have so far. So this is equivalent to saying that we have g of z, which is 1 minus e to the minus 2z tau minus tau squared, and this is equal to g of z plus tau. So just plugging z plus tau right in over here, we're going to get 1 minus e to the minus 2 z plus tau times tau minus tau squared. And what does this right hand side evaluate to? Well, it's going to be equal to 1 minus, I'm going to do a bit of expansion over here. This is going to be e to the minus. First of all, we have 2 times z times tau. So 2z tau. I'm going to write this minus tau squared next. And then finally, we're going to multiply by this second term in here. So minus 2 times tau, which is minus 2 tau squared. Alright, and we can use some exponential properties again to split this up. So we can have a multiplication by e to the minus 2 tau squared over here as well. And notice one thing, we have 1. So 1, we have 1 over here, we have a minus over here, we have e to the minus 2z tau minus tau squared, which is exactly what we have over here. And on the right hand side, all that's really added is this extra factor of e to the minus 2 tau squared. And in order for the left hand side to be equal to the right hand side, we require that this extra factor is equal to 1, because anything else, and well, g is no longer periodic in tau. So now we have the requirements that e to the minus 2 tau squared is equal to 1. And to figure out what tau is equal to from here, remember tau is a complex number, let's rewrite 1 as being e to the 2 pi I times k, where k is an integer. And from here, well, we can compare exponents. So what are we going to get? Well, we're going to get minus 2 tau squared is equal to 2 pi times I times k. And we can divide both sides by 2. So we're going to get tau squared is equal to pi times I times k. And if we bring this negative over and combine it into this k, for example, it's still going to be an integer, so we can kind of ignore this negative. And finally, we can take the square root on both sides, and tau is equal to the square root of pi times I times k. And remember, k is an integer. And what k should we pick? Well, let's just pick the simplest non-zero solution for k. If we pick k is equal to 0, then, well, what actually happens is our rectangle is just a line that's traversed in opposite directions, which isn't really helpful. And k being equal to 2, 3, 4, well, it's just going to make our lives a little bit harder. You can choose those values, it's going to work out the same way, but why do that when you can just let k be equal to 1? And, well, we find the final value for tau, which is going to be the square root of pi times I. You can rewrite the square root of I in polar form if you want to, but I'm just going to keep it like that for now. So if we use its definition for tau, I'll put it over here. So tau is equal to the square root of pi times I. We can figure out what our final expression for g is equal to, and then we can figure out what our f of z is equal to. So let's plug everything in. So at the moment, let's figure out what g of z is equal to first. So g of z is now equal to 1 minus e to the minus 2z times a tau. And then we have a minus tau squared. So that's e to the minus tau squared. But notice tau squared is equal to pi times I. Just squaring both sides, cancelling out that square root. And, well, if tau squared is pi times I, or I times pi, this row over here is negative 1. And that's going to switch this negative into a positive. So g of z is equal to 1 plus e to the minus 2z tau. Alright, great. And now let's finally plug it into our f of z. So f of z, let's get rid of this ugly g of z. This f of z is now equal to e to the minus z squared. Remember, we still had this Gaussian function at the top. And then we divide it by our function g of z. And that's going to give us 1 minus e to the minus 2z tau. And remember that extra tau squared there, that just gave us a positive. So in fact here should be a positive. Alright, and this is our function f of z. That took a while to finally figure out a suitable function f of z to use that works for this. But we have a function f of z now, so things should be pretty straightforward from here. So tau is pi times I. Accidentally rubbed that out. Alright, so we figured out what our function f of z is equal to. Let's immediately figure out what the poles are, because our poles will be very useful in determining what our residue will be. So poles of our function f of z, let's solve a 1 plus e to the minus 2z tau is equal to 0. And that means that e to the minus 2z tau is equal to minus 1. We can write this a little bit nicer in polar form as being e to the I pi times some odd integer, so 2k plus 1, where k is an integer. And, well, we can compare exponents over here, so minus 2z tau is equal to I times pi times 2k plus 1. And I'm going to rewrite tau as the square root of I times pi, or pi times I. You can probably see y over here. And now, in order to figure out the solutions for z, let's isolate it. So divide both sides by square root of I pi. We're going to get square root of pi times I, which is tau. So this is going to be tau on the right hand side. Let's divide it by 2 as well. So tau divided by 2. And let's distribute this negative into this expression for odd integers. A negative odd integer will still be the same as an odd integer, so we still have 2k plus 1. So in fact, we get infinitely many poles for this function, and that should be quite obvious because we have an exponential function. It's a periodic function in the complex plane, so no surprise there. We have infinitely many poles. And what poles do we choose exactly? So our poles will be every odd multiple of tau over 2. But which ones do we really care about? Well, the only pole we care about will be z is equal to tau over 2. So just letting k be equal to 0 over here. Reason why is because if you look on our contour, I should have probably explained this earlier, but we have r plus I times b, and remember we called I times b, we renamed it as being tau. So in fact, since tau isn't purely imaginary, our rectangle is technically kind of like a parallelogram like so, but that doesn't really matter. We can just still consider a simple rectangle. Reason being is because on the top path over here, we're going from minus infinity to infinity eventually, and it doesn't matter if we shift it by some finite amount. You can justify that by looking at the integral, just doing a substitution to adjust the shift over here back into a rectangle, and then the bounds won't change. It's still going to go from minus infinity to infinity. So for our contour, our b value should really just be the imaginary part of tau. So we're going to, I'll squeeze it in over here, we're going to let b be equal to the imaginary part of tau. And if the height over here is imaginary part of tau, and we have a tau over 2, well, the imaginary part of tau over 2 will be, well, directly in the middle of these two upper and lower parts. It's going to be nicely sandwiched in between. And notice tau is the square root of pi times I, so it's going to lie on the line y equals x, because square root of I is e to the I pi on 4, and that's exactly 45 degrees. So y equals x, and then you have all these other poles that are at every single odd multiple of tau over 2. So this pole over here is going to be tau over 2. Alright, so we know what pole we're dealing with. We're just dealing with the pole tau over 2. And now remember at the start of the video, we assumed that the integral over gamma 2 and the integral over gamma 4 vanish as r approaches infinity. Let's in fact show that that is the case for this function f of z, because if it's not, we clearly can't evaluate it using the residue theorem or anything like that. So in this next section, let's take a look at the integral of over gamma 2 of f of z dz, and we want to show that in the limit this goes to 0. So let's estimate this by putting absolute values everywhere. And let's first of all, plug in the definition of f of z. That's going to be e to the minus z squared over 1 plus e to the minus 2z tau dz. And well, we can parameterize this part. It's just a straight line segment going from an imaginary part of 0 to an imaginary part of tau. Speaking of which, let's figure out what the imaginary part of tau is equal to. So we know tau, we can rewrite it as being, let's see, the square root of pi times e to the I pi over 4. And what we can express this in Cartesian form. So tau is equal to the square root of pi times 1 over the square root of 2 plus I over the square root of 2. And clearly you can see that the imaginary part of tau is going to be the square root of pi divided by the square root of 2, or the square root of pi over 2. So in fact, this line over here, we can say that it's y is equal to the square root of pi over 2 if you want. And yeah, let's just try to parameterize this. So we know that we can make the substitution z is equal to, well, we're fixing the real part, which is going to be r, and then we're going to add I times t, and t is going to go from 0 to the square root of pi over 2, which is the imaginary part of this top line, and dz is going to be equal to I times dt. Pretty straightforward stuff. Let's plug everything in. So we're going to get now the absolute value of the integral from, now t is going to go from 0 to square root of pi over 2, so 0 to square root of pi over 2. And then we have our f of z. Let's plug z is equal to r plus it into everywhere. So we're going to have e to the minus r plus I times t, but the whole thing squared, divided by 1 plus e to the minus 2. Z is going to be r plus I times t times tau. and this is integrated with respect to t, so we're going to have I times t as well, and ends up absolute value. And notice now we're integrating with respect to a real variable, so let's use the integral inequality, and we can say this is less than or equal to the integral of the inequality. So we're going to have the integral from 0 to the square root of a pi over 2. We are going to get as well e to the minus, let's use the binomial theorem over here, so we're going to have r squared first, and minus r squared, and then 2 times r times it, but since we have minus, we have minus 2r it, and then finally over here, I times t, but the whole thing squared is exactly minus t squared, and we have a minus out here, so those are going to cancel, giving us a plus t squared, and this is in absolute values as well, and we're going to divide this all by the absolute value of 1 plus e to the minus, I'm going to write it as 2 tau, and then r plus it. We'll worry about what this denominator will turn out being equal to later on. Absolute value of I is 1, and we're just left with a dt. Alright, and now let's use some exponential properties out here to split it up. We're going to have e to the minus r squared, e to the minus 2rit, but notice we have an imaginary unit over here. 2 is real, r is real, t is also real, it's on this real interval. So whenever you have e to the real times I, the absolute value of that will be equal to 1, so we can kind of ignore this. And then we also have e to the t squared over here. So on the top, this is going to end up being equal to the integral from 0 to the square root of pi over 2. And on the top, we're going to be left with e to the minus r squared, and then plus a t squared. And we can put absolute values over here, but because the exponential function is always positive, we don't need to worry about that. And we can still divide this by. And now at the bottom over here, we want to use something called the reverse triangle inequality. And what does that say? It says that if we have, let's separate this a little bit. If we have the absolute value of a minus b, this is going to be greater than or equal to the absolute value of a minus the absolute value of b. And this is useful for the denominator, because if we can show that this is bigger than something else, and taking the reciprocal, we're showing that it's less than something else, so hence finding a new upper bounds. So we want to express this denominator in the form a minus b, and there's an easy way to do that. We just replace this plus with a double negative, so minus this exponential function, if you want to put it that way. And what we can just apply this reverse triangle inequality. If you want, you can think about it as the reciprocal of the reverse triangle inequality, so 1 over the absolute value of a minus b is less than or equal to 1 over the absolute value of a minus absolute value of b. And in fact, this equal sign should have been a less than or equal to, because we're finding a new upper bound for this whole entire integrand. So we're going to get now the absolute value of the absolute value of a, which is just 1, and we're going to subtract off the absolute value of this exponential function. And we also have a negative in here, that kind of drops off. So we're going to find the absolute value of e to the minus 2 tau. Let's expand out a little bit, so minus 2 tau r, and then e to the minus 2 tau times I times t, like so. And this is integrated with respect to t. So a lot going on the denominator, but there's some nice simplifications we can do, because notice tau is complex, so especially for this first factor, we can ignore the imaginary parts of tau, because then we're going to end up with something in the form e to the real number times I, and taking the absolute value of that is going to be 1. So for this first factor, we're only interested in the real part, because that won't vanish in the absolute value. So this is going to be the integral from 0 to the square root of pi over 2 e to the minus r squared plus a t squared divided by, now we have the absolute value of 1 minus, and all that's left for this first factor is just going to be the real part of tau. And the real part of tau, let's see over here, it's going to be the square root of pi over the square root of 2, well, this is also the real part of tau as well. So we're going to end up with minus 2 square root of pi over 2 times r That's going to be all that's left from the first factor. And for the second factor, it's going to be a little bit more tricky because we have an extra I. So in fact, the real part of tau, well, we're still going to get the form e to the I times real. So in fact, for the second factor, we only care about the imaginary part of tau, which happens to be the same thing as the real part. So we're going to get e to the minus 2 times the square root of pi over 2. And then we have I times t. But I times I is -1. That can cancel out over here. So we're just left with this expression over here. This is integrated with respects to t. And obviously you can put an absolute value here if you want to. And now I want you to notice one thing. In the limit as our r approaches infinity, notice that t is finite, so t squared is also finite because it's on this interval. So mainly we're going to be taking a look at this r squared. As r approaches infinity, as it grows bigger and bigger and bigger, we're going to get e to a very, very negative number, and that's going to approach 0. So this whole entire numerator will approach 0 in the limit. And how about the denominator? What's going to happen? Well, again, t is finite over here, and well, this thing here is finite. And how about over here? Well, as r approaches infinity, this exponent will become more and more negative, and whatever we have over here, that's just going to approach 0. So in fact, the numerator approaches 0 and the denominator also becomes finite. So in fact, this integral just evaluates to 0 in the limit. So what did we just find out over here? Notice we always use the less than or equal to inequality. So tracing back that chain of inequalities, we can conclude that the integral over gamma 2 in absolute values is going to be less than or equal to, so less than or equal to 0 in the limits as our r approaches infinity. So I'll write this out properly. In the limits as our r approaches infinity, the absolute value of the integral over gamma 2 is going to be less than 0, and that just implies that the integral over gamma 2 itself, in the limits of course, so limit as r approaches infinity goes to 0. So we can safely cross out this integral. It's going to go to 0. Now we're going to do the exact same process for gamma 4, so the integral over gamma 4. So let's take a look at that. The integral over gamma 4, again, we want to estimate this thing, find some kinds of upper bounds for it. Let's plug in our function f of z, so this is the absolute value, integral over gamma 4 of e to the minus z squared over 1 plus e to the minus 2z times tau dz. And well, again, we're going to do a bit of a parameterization. We can notice that on this gamma 4 that's going down, z, well, we're fixing the real part, which is minus r, and then we're just varying the imaginary part. So we're going to add I times t, and t is going to go from up here, which is square root of pi over 2, down to 0. And of course, dz is equal to I times dt. So let's plug everything in. This is going to be equal now to the absolute value of the integral. T is going to go from up here, which is the square root of pi over 2, down to 0. And we're going to have, well, let's plug minus r plus it into all these z's. We're going to have e to the minus r plus it, but the whole thing squared, divided by 1 plus e to the minus 2. Z is minus r plus it, and this is multiplied by tau. And we have our dz, which just turns into I times dt. And notice again, we have a real variable we're dealing with, so we can use the integral inequality. We can actually reorient this integral as well to go from 0 to square root of pi over 2, introducing a negative there, but that negative will disappear in these absolute values anyway, so it doesn't really matter. We have the integral from 0 to the square root of pi over 2 of the absolute value of the top, so absolute value of e to the r squared, and then we have, let's see, 2 times minus r times it, that's going to be minus 2r it, because we have negative out here as well. We have 2 times r times I times t, and then of course over here, I times t squared is negative t squared. We have a negative, so let's add it t squared. Ends at absolute value, and we're going to divide this through by the absolute value of the denominator. That's going to be 1 plus, might as well expand things out over here, so we're going to have e to the 2 times r times tau. That's the first term in here. And for the second term, we're going to get e to the minus 2 times I times t times tau. That's a mouthful. That should be correct, and ends of absolute value, of course. Absolute value of I is 1, and then we end off with the dt. Alright, and just like before, this r squared is real, this t squared is real, and over here on this second term over here, we have something in the form real number times I, and e to the real number times I inside of absolute value. That's going to be equal to 1, so let's forget about that. And we're going to use the reverse triangle inequality down here as well later on. So now, so far, we have the integral from 0 to the square root of pi over 2 of e to the r squared plus t squared. I just realized as well, we should have had minus r squared, because minus r squared is r squared, and we have a negative here. So technically this should have been an extra negative in here, so negative, otherwise this integral won't vanish. And we divide this through by, and again we can interpret this positive as a negative negative, so negative negative. And using this inequality over here again, we can say that it's equal to 1 minus, technically absolute values, so 1 minus absolute value of this stuff, and this is going to be equal to the absolute value of, now same deal as before, we only, for the first factor here, we only care about the real part of tau, because the imaginary part in that exponential function will vanish. So we're just going to be left with e to the 2 times r times the square root of pi over 2. That's the real part. And for the second factor, we only care about the imaginary part, because the real part will vanish. So we're going to have e to the minus 2 times I times t, and imaginary part of tau is I times the square root of pi over 2. So this is a big mess, but notice I times I over here is negative 1. That's going to cancel out nicely with the negative at the front, so we're just going to have 2t times this constant. Alright, great, and notice, just like before, we have t squared, which is finite, and as our r gets bigger and bigger and bigger, we have an exponent that's getting smaller, so this whole entire numerator, that's going to approach 0 as r approaches infinity. And notice on the denominator, even though we don't have a minus r over here to make this second term go to 0, in fact what actually happens is that r gets really big, this whole entire second term gets really big. 1 minus a big term is still a big term, but negative. But since we have absolute values, this whole entire denominator will go to infinity. And as you can see, we have a 0 divided by infinity situation, which clearly in the limit goes to 0. So hence we've shown that for the integral over gamma 4, in the limit, we're going to get a 0. So we can say that the limit as r approaches infinity, using those chain of inequalities again, of the absolute value of the integral over gamma 4 is less than or equal to 0, which just means that the integral over gamma 4 is equal to 0 in the limits, of course. So we can safely cross out the integral over gamma 4 and say that that goes to 0 in the limit. So we've come quite far. So far we've shown that these two integrals go to 0. We've shown that the integral over gamma 1 plus gamma 3 evaluates to the Gaussian integral, which is the integral from minus infinity to infinity of minus e to the minus x squared dx. Because remember, from these two integrals, we had this function over here, which we really wanted to be equal to that Gaussian integrand. And all that's really left for us to do is to calculate 2 pi I times the sum of residues. So this Gaussian integral that we have so far, we can now safely say that it's equal to 2 pi I. We only have one residue in here, so that's going to be 2 pi I times the residue at z being equal to tau over 2 of our function f of z. So as you can see, all that work leads up to this equation over here, that the Gaussian integral, we can just calculate it by figuring out the residue at this pole tau over 2. And let's do that. It shouldn't be too hard. So this is now equal to 2 pi I. This is going to give us a simple pole, in fact. You can check that for yourself, because if you differentiate the denominator and plug in tau over 2, you won't get a 0. So we're going to have the limit as z approaches tau over 2. So as z approaches the pole of z minus the pole, so z minus tau over 2 times our function, which is e to the minus z squared, divided by 1 plus e to the minus 2z tau. Alright, now what I'm going to do is split up the limits, because notice as z approaches tau on 2 in this factor, it's going to go to 0. And since tau over 2 was a 0 of this denominator function, this denominator will also go to 0. So we have a 0 divided by 0 situation. Isn't too great, so let's use Lopital's rule. So we have 2 pi I. We have the limits as z approaches tau over 2 of z minus tau over 2 divided by 1 plus e to the minus 2z tau. That's the first limit, and we also have the limits as z approaches tau over 2 of e to the minus z squared. And let's figure out this limit. Remember, that's a 0 divided by 0 situation, so let's differentiate the top and the bottom using Lopital's rule. So we're going to have the limit as z approaches tau over 2. Derivative of the top, that's going to be 1. It's a linear function with a leading coefficient of 1. That's going to be 1. And then derivative of the bottom, well, derivative of 1 is 0. And then derivative of this exponential function, we can just use some chain rule, it's not too bad. It's going to be minus 2 tau times e to the minus 2z tau. So just differentiating with respects to z. So that's the first limit, almost done. And let's evaluate the second limit. It's going to give us e to the minus. Now plugging tau over 2 into the z, we're going to get tau squared divided by 4. Alright, so let's keep going. This is now going to give us 2 pi I. Now if we plug tau over 2 into here, what are we going to get? We're going to get 1 divided by minus 2 times tau times e to the minus 2. And now z becomes tau over 2. So that's going to be tau squared divided by 2, because we're multiplying by this extra tau. And over here we still have e to the minus tau squared over 4, which I'll just write up here. Alright, very nice. And let's see what we can do now. We have a 2 and a 2 that will cancel. And we're left with, let's bring this negative up. So we're left with minus pi times I. And then notice we have a tau that's divided through. That's interesting. We have a tau down here. And then we have e to the minus tau squared over 4 divided by, now 2 and 2 over here will cancel out, leaving us with e to the minus tau squared. And we're running a bit low on space, so let's just dump everything up here, I guess, and we'll just finish off there. So remember, all these are still equal to each other. So now this is equal to, let's see, remember tau was the square root of pi times I. So we're going to get minus pi times I divided by the square root of pi times I. This is getting a little bit more Gaussian here, and let's see what we have over here. Let's multiply the top and the bottom by e to the tau squared. So e to the tau squared, e to the tau squared. These two will cancel out because their exponents are negatives of each other. And let's see what we have over here. Tau squared minus tau squared over 4. That's going to give us e to the 3 tau squared over 4. And to remember, tau squared is equal to pi times I. And let's see, this is going to give us, well, so far we have a minus the square root of pi times I. And then we have e to the, well, tau squared, remember, pi times I. So I times 3 pi over 4. And, well, let's rewrite this a little bit. This is a minus the square root of pi times the square root of I times e to the I 3 pi over 4, and let's rub this out. And well, let's express square root of I in polar form. That's going to be square root of pi e to the I pi over 4, and then e to the I 3 pi over 4, and this is equal to minus the square root of pi e to the I times pi. E to the I times pi is negative 1. So this is minus the square root of pi times minus 1. Minus 1 and negative over here will cancel each other out. And we end up with the final value of the square root of pi. That's really, really cool. So yeah, that's basically it for this whole entire video. We've shown that the Gaussian integral is equal to the square root of pi. By far the most exotic way I've seen so far to evaluate a real improper integral using complex analysis and contour integrals. We had to do all that stuff with assuming things about functions and finding out what that function is under those assumptions. So yeah, really cool stuff. This is something you don't see that often. So yeah, hopefully you guys enjoyed this as much as I did. Make sure you subscribe for more content like this. And until the next video, I hope you guys have a wonderful day, and I'll see everyone later. Bye bye.